This is our Fed final presentation, and this is our group.
I'm Mark Wu. I was the researcher for this project.
I am Talmadge Bevacqua. I was the build and materials manager for this project.
And I'm Alex Kellogg. I was the project manager and contact to teachers.
Alright, so we're going to show you an overview of the project now. First, we are going to start at the end of the probe, where we connected to the voltmeter using alligator clips that were bought from Radio Shack. Right here, you got your negative and your positive leads. At the end, or as we move down, you can see that we bought 16 gauge speaker wire to connect to the photodiode or solar panel that we used here. And as it leads down, you come to the actual probe part of the project. We used a screw off cap right here, and we tied a knot in the wire so that it would not jerk the wire out of the end of the probe and cause a failure, where we soldered the solar panel onto the wire. And you can see that it is threaded on both sides right here, and we used right here where the pipe meets the coupling right here, we used Plumber's glue to connect all of our fittings together. Okay, as we move down the project, we used a 10-foot long PVC pipe that was 1 inch in diameter. After the project was over, we cut it in 3 pieces so that it was easy to maneuver. Moving down the end of the pipe, you get to the sensor end of the probe. You can see here where we expanded the pipe out using fittings and couplings right here, male and female adapters, that leads to a threaded edge right here. As you reach the sensor part of the probe, you can see that we used a photocell or a solar cell instead of a photodiode. We chose this option because an actual solar cell does not require an external power source like the photodiode does. You can see here, leading up to the solar cell, we chose to use lead wires to actually connect to the solar cell because of the small soldering points on the actual solar cell, and then soldered them onto the 16 gauge speaker wire. After that, we included Teflon tape here to seal it off so that water would not leak in. As we come to the lens, you can see it is also threaded. We connected to the rest of the pipe. This, we used a plexiglass lens right here, where we sealed it on both sides with a silicon based caulk that is waterproof on both sides.
Before we started construction of the nuclear probe, we needed to find background information out about Cherenkov radiation. We found that Cherenkov radiation is electromagnetic radiation that is emitted when electron particles pass through an insulator at a constant speed. The effect of this is water particles enter an excited state and emit a blue light when energy is released. The theory is that the intensity of the blue light, or Cherenkov radiation, is directly proportional to the power of the reactor.
During the construction phase of the project, we tested our sensor using LEDs and flashlights. Then on the official test day at Burlington Labs, we inserted the probe into the reactor pool and used voltmeters to obtain readings on the light intensity. Using our results from our official test at Burlington Labs, we were able to calculate the unknown power level that the nuclear reactor was running at. We estimated this to be at 1,415 kilowatts. In actuality, the reactor was only running at 610 kilowatts. Our percent error was greater than 100%.
Now we move on to the design cycle. The first step in the design cycle was to identify the problem.
For this project, we were given the task to calculate an unknown power level of a nuclear reactor by measuring the intensity of blue light or Cherenkov radiation that is being emitted during the reaction.
The next step in the design cycle is to search for solutions. We found out through online research that the light intensity could be measured through photodiodes, phototransistors, or photovoltaics. After that, we had to narrow and select one of those three sensors to use in our project. We determined that photodiodes were unusable because they require an external power source, and phototransistors were not accurate enough for our project. So we decided to use a photovoltaic cell, which is also known as a solar cell.
The next step is to build, and so we spent countless hours putting together the probe and making modifications. The final step is to test the probe. To do this, we used LEDs and flashlights and shined them on the solar cell to see if we could get any readings.
Moving on to advice for freshmen. You should start early on this project, as dates will creep up on you quickly and you will be scrambling near the deadlines in order to get everything done. Luckily, this didn't happen to us. We were organized and prepared for each deadline. Also, another important factor to remember is shipping for parts.
The things that we would do differently. First off, we would have ordered our parts sooner. The second thing we would do differently is, originally we had the design where we screwed this coupling onto the bottom in order to be able to service the certain sensors that we were using and or change them. But once we determined that we were going to use the solar cell, we should have sealed the seal with some sort of silicone instead of keeping the Teflon tape, because this would have ensured that we would have had a tighter seal.
At the end of this project, we have come to the conclusion that this project was successful. Through the design cycle, we learned much about how an engineer goes about doing projects such as this. We would like to thank Burlington Labs for letting us spend time there.